So when we were talking about limits way back when we did, some of the things that we discussed were those fancy, you know, what do we call those? Those interesting limits. So for example, in this limit here, if I was to substitute, I would have gotten a 0 over 0 situation. And you remember I said that's for you to go, oh, something more interesting might be happening. I've got to try to do some techniques on this. So for the first one, I'll just quickly show you how we would have approached this question in case you've forgotten. But of course, I don't have enough space quite there, so I'll redo it for you. It would be the limit as x goes to -1. And what we would have done is we would have applied a little bit of algebra. Hopefully it's going to look familiar to you. And we would have tried factoring this out. So we would have had the limit as x goes to -1 of 2x plus 1 x minus 1 over x plus 1. And then we could have said those would disappear, and I would have the limit as x goes to -1 of 2x minus, that's just messy, let me try that again, of 2x minus 1. So that would be 2 times -2. So we would get a number. We'd say, hey, that's -4. Right? That's the world we came from, and that's the technique we used. Today we're going to look at how this new rule, Hopital's rule, can help us out in an easier way. Another thing that we had talked about was this situation here. When we had infinity over infinity, if we tried to substitute, that's another interesting one where we say, well, we don't know which infinity is bigger, smaller. Maybe this one of them wins. Maybe they have an asymptote, right? But the point is we had some more work to do when we saw these. So we call these ones the indeterminate forms, and they're the special cases like 0 over 0 and infinity over infinity. Can anybody think of one that might be also interesting? What might come up and you say, oh, I don't know about that. Maybe it's not. Well, if you got a St. Bernard out of this, yeah, that'd be pretty weird. But what would you think about, you know, maybe can you come up with one that you might get as your limit and go, geez, maybe that needs extra exploration. I know. Well, what about something like this? Who wins? 0 times infinity, right? Who would win in that case? Well, we don't know. It might be more interesting. And just to give you an idea where we're headed, the reason this one might also be interesting, we could think of that as infinity over 1 divided by 0. So then it's the case that it's still an infinity over infinity. So when we find these special cases, we're going to try to write them in that form where it's 0 over 0 or infinity over infinity, the ones we've already worked with. So if you got your graphing calculators, we're going to take a look at this next one here. So if you could pull those out. Okay, so I'm going to put the graph into this one so you can see it up on the board. But you should try putting that equation in. Another technique we talked about for limits was we could look at them graphically and try to get an idea from what the graph is doing. So this one would be y equals e to the 2x minus 1 all divided by x. And we get this picture here. So as x approaches 0, this would divide by 0. Obviously, it'd be some algebraic problems. But in terms of calculus, what limit would you expect to find? As x approaches to 0. Yeah, the graph here, it appears like it's moving towards 2. So as x approaches 0, on one side, here's where I'm approaching, and I'm getting right in at that number 2. Same thing as I approach from the other side. Okay. So from both sides, it's approaching 2. So what I'll just copy that into the, it about looks like this on our screen. So from either side, the limit as x goes to 0, we would guess graphically that the limit for this expression would be 2. How else might we do this if not graphically or using some of those fancy techniques? Do you remember another technique that we used? Still a calculator one. Yeah, a table will work well too. So the table would show us the same thing here. Now, let's talk about how L'Hopital's can do all of these things with one technique. Okay? So first we need to know, what is L'Hopital's rule? Well, L'Hopital's rule...
That's a rule invented by L'Hopital.
That's a good guess. L'Hopital's rule, the key thing here is it works for these indeterminate forms. Okay? L'Hopital's rule doesn't work for everything. It only works when we have these strange cases, like 0 divided by 0, infinity divided by infinity. So what I'm going to do here is I'm going to say that if that's the, if that's the case, then the limit for this form is the same thing as the limit of the derivative of f divided by the derivative of g. So we can take the derivatives in order to find another way to get the limit. And it may be easier with the derivative than the function, especially when you think of polynomials, because they start to get smaller and smaller. So for example, if you start with x cubed, you can cut it down to 3x squared. Then you can cut it down to 6x. Then you can cut it down to 6. Taking derivatives may make life easier for you. So let's try this then, the one that we just did graphically. Let's try this using L'Hopital's rule. So first thing we have to do is we need to know, is this one of these special cases? So we got to directly substitute this in. I'm going to get e to the 0 minus 1 over 0. 1 minus 1 over 0. So 0 divided by 0. Yep, L'Hopital's rule does apply to this function. So the way I'm going to rewrite it is now I'm going to look for the limit as x goes to 0. So what's the derivative of the top? Almost your favorite derivative. What do you get? Times? Yep. So 2e to the 2x is the derivative of the top. And, all right, shy people, here you can impress me now. What's the derivative of the bottom?
1.
Oh, good, 1. So you are alive out there. Now, can we do this directly?
I guess.
Okay, let's find out. So this will be 2e to the 2 times 0 over 1. So that'll just be 2. And that's the same thing up here that our graph showed us, but now we've been able to do it without a graph or a calculator using L'Hopital's rule. Okay. So L'Hopital's rule is very versatile. It would work in all those situations we've done so far with one technique. So what I'd like you to try is, here's a situation. First of all, does L'Hopital's rule apply here? If it does, use it to find the limit. So what do we think? Does L'Hopital's rule apply here? Is this an indeterminate form? Hands up if you think this is an indeterminate form. Couple people? Okay, so if it is an indeterminate form, then which one do you think it is?
Infinity.
Infinity over infinity, yeah. So if you put natural log x, as x goes to infinity, that's going to be infinity, and plain x is easy, it would be infinity over infinity. So this is a case where L'Hopital's rule will work. So I can rewrite this as the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. So this is the limit as x goes to infinity of 1 over x. Can anybody figure that out? Remember how it works? Yeah, it's 0, right? That infinity just obliterates that 1 until nothing's left. So there we are, the limit is 0. I'm not sure we know any algebraic techniques to do this, right? Because what else would you do with a natural log? Okay. How about here? What do you think? Does this apply? Will we have infinity over infinity, 0 over 0? Is this one of those indeterminate forms? So what happens on top? What happens on top? Like, is it 3? What happens to the limit for the top of that fraction?
2x.
Oh, you've already gone a step ahead. I just want to know, does L'Hopital's rule apply here?
Considering that they're on the bottom, we have a negative exponent, I'm going to say no.
Okay, so it could be the negative exponent is throwing you for a bit. Well, let's try putting it in and see what happens. So as I head towards negative infinity, this will be negative infinity squared over e to the negative infinity. So what kind of situation do you think you have here? Oh, be careful, because that negative becomes a positive. So you actually have infinity on the top and infinity on the bottom. So we don't know yet which one is going to win. So let's try it and see what happens. If I rewrite this, it's going to be the limit as x goes to negative infinity of 2x over negative e to the negative x. Can we figure out this derivative? We're not doing the derivative of the entire thing. It's the derivative of each piece, top and bottom. That's a good point. This isn't quotient rule. We're looking at it as two pieces. Like, this is the first piece on top, and this is the second piece on the bottom. So we end up with two derivatives. So it's easier than quotient rule. We're taking the derivative of each piece. So what happens in this situation? Is this something I can figure out by substitution? How come, Danny? Okay, so you're correct. This is still infinity over infinity. So does that mean we're done? Just do it again. Yeah, why not? So it still applies. The derivative of the top now is going to be 2. The derivative of the bottom is going to be e to the negative x. So can I do this by direct substitution now? Okay. So that'll be e to the infinity. So this will be a 2 over infinity, which means nothing's left. It's 0, okay? But again, it's something that L'Hopital's rule can do for us that would be quite challenging without it. Okay. Are there any questions so far with applying L'Hopital's rule?
Oh, applying L'Hopital's
Can I just, if 5 is 5, I'm really confused, and 1 is I get this is easy. How well do you think you can recognize if L'Hopital's rule applies? That's all. I'm not asking about the question. Can you recognize that L'Hopital's rule applies to this question? 5, I'm super confused. 1, it's easy. Okay. So a couple of you may have some questions. What I'm going to do then is, before we talk about some other strategies, we'll do one more, and then I'm going to let you do a bit of homework to kind of digest it, and then we'll come back to this. But try this one on your own here and see if you can figure out what you would do, okay? And then we'll take a short break. So if we substitute in, what's your initial value? What do you get when you first substitute in this infinity for x? What do you think? Yeah, that's right. So if we were to do that, we would get 0 times infinity. And again, that's one of those interesting situations. So I've highlighted a few other forms that you may come across. For example, these ones here are other forms that we'll try. Some of them may look obvious. Some of them you may say, why is that an indeterminate form? Like, for example, 1 to the infinity. Shouldn't that just be 1? Well, we'll see later that it may not be. Or what about infinity to the 0? Right? There's some strangeness in these answers. Just so you know, after this example, we'll be looking at your first year university. I'll stick to relatively recognizable 0 over 0, infinity over infinities. But next year, you know, UBC, SFU, etc. We'll probably expect you to go to the examples that we're about to do here a little further. Okay, but for today, anyways, we should be able to do this one we've just started. So that doesn't quite look like L'Hopital's rule yet. Does anybody have any bright ideas? Sure, Lily? Yeah, so why don't we go like this instead and say limit as x goes to infinity of square root x over e to the x. Now the situation I have is infinity over infinity. So L'Hopital's rule will apply. So I take the derivative of the top and the derivative of the bottom. So this will be 1 over 2 root x divided by e to the x. And before I give up all hope and think that there's more infinities and things, we normally wouldn't want to do a question that looked like this. There's too many fractions in there. We would want to make this nice and simplified as possible before we went on. So hopefully, before you started thinking about that limit, you try to simplify this. Okay. Now what do you think that happens to that limit?
It explodes.
Close. Well, what happens to the top as x goes to infinity? Does it grow at all? Does it change?
It shrinks.
Does it shrink? It just stays the same.
Oh,
So the top is the same, yet the bottom is?
a barrel roll.
What happens to the bottom of the fraction here? Say it, I heard it.
It becomes unstable. It eventually implodes.
It is. Right? As x goes to infinity in these pieces, that's going to become an infinite number itself. It's huge, right? 2 times the square root of infinity times e to the to infinity. That's just a gigantic number. So that means it's going to be 1 over infinity. So any constant divided by infinity is 0. So at this point, what I'm going to do is I'm going to get you to take a look at some homework questions just to practice them, and then we'll try a few advanced ones in about 20 minutes, half an hour. So I'll just show you here for homework. So let's, you're going to have to bear with me a little bit as we do these few. These would be like genius for you to come up with it on your own. To be in all honesty, I wouldn't be able to do this sort of stuff on my own, or I'd be way more famous than a math teacher at high school, right? Not to knock math teachers at high school. But, again, the point is there are some really advanced techniques that you can do with L'Hopital's rule, and I'm just going to illustrate a couple to you. So the first one we're going to prove, I've given you a little hint there, but I'm going to have to do it on another slide because I'd like to make sure it's presented with enough room that it doesn't look all cluttered and messy. So the limit as x goes to infinity of 1 plus 1 over x to the x. That's what we're going to look at. So of all the problems here, what do you think, if you could change just one thing, what would you like to do to this? What makes it difficult to work with? The fraction? Well, can you figure out the limit for that fraction? Yeah, it'd be 0. I mean, when I look at it, I think there's something there that kind of makes me go, oh, it's hard to figure out what I'm going to do. The exponent, right? Anybody figure out if this is our problem, how could we move that exponent? Do we know anything that could move an exponent? Logs? That's where we're headed. So that's the idea here. You'll have to bear with me to see how I'm going to do it. But basically what I'm going to do is, first I'm going to assume that it exists. And I'm going to say, let's assume that that value is y. Okay, so we'll say it is a real number, and let's just call it y since we don't know what it is. And now we all agreed that logs would be nice here, so let's take a look. What would happen if I was to do that? Okay. Now, the nice thing about using the log there is, of course, I can move that exponent down to the front. And if I was to substitute this in, I would have a 0 times infinity situation. Technically, it would be a 0 times 0 situation. Right, the log at 1 would just be 0. So it doesn't really give me an indeterminate form yet, but what I could, that's the problem, Mr. Joyce, wake up. That's the problem. It should be infinity times 0. Now it looks like a L'Hopital's rule question. So to make this thing an indeterminate form that we want to work with, I need this fraction. So I'm going to say, let's work with it like this. The limit as x goes to infinity of the natural log of 1 plus 1 over x divided by 1 over x. In this case, it's going to be a 0 over 0 situation. So now I can use L'Hopital's rule. Okay, so let's see where we would go with L'Hopital's rule. This would be the limit as x goes to infinity. And for the log, it'll be 1 over 1 plus 1 over x. And the derivative of the inside, this is the inside function here. So the derivative of the inside is going to be negative 1 over x squared. And the derivative of the bottom, this piece right here, is going to be negative 1 over x squared. So you can see one nice thing happens. This piece would factor out, so it would be gone, gone. And now I end up with the limit as x goes to infinity of 1 over 1 plus 1 over x. Which was just what was left over here. That's where it came from. It's the only piece that wasn't factored out. As that goes to infinity, that piece becomes 0. So that means it must be equal to 1. But this is what I found. Natural log of y equals 1. So if that's true, natural log y equals 1, what's the value for y? E, yeah. So it would be e to the 1 equals y. So y must be equal to e. So that's what the limit is here. Whoops, wrong spot. That's what the limit is here. It's equal to Euler's number. That's the definition for Euler's number. So again, some very brilliant people did this the first time. Not that you're not all brilliant people as well, but that'd be pretty scary and that'd be pretty tough to encounter. But this technique of using a natural log to help do away with exponents, it's another thing that you may encounter later in your calculus world. So I'm going to do one more with the natural log. Do people need another minute to write in that example? Maybe I'll leave that just for a minute for you. Okay. So the last one that we'll do with this natural log technique, and I guess I should mention, sorry, here, that this indeterminate form would be 1 to the infinity, which is kind of surprising that 1 times 1 times 1 times 1 times 1 times 1, well, in this particular case, it doesn't actually equal to 1. Because remember, this only approaches 0. There's always actually a little tiny piece there. It doesn't actually ever get to 0. So if it's like 1.00000000000000001, there's still that little piece left over, and that's why when we multiply it up, it doesn't actually turn out to be 1. Okay, in this situation, anybody remember the sign of 0? So you go over here.
0.
Yeah, sign of 0 is 0.
Regardless of the calculator mode.
So it would be 0 to the 0. Which again is one of those forms where we may have to work a little harder at, because 0 times 0, 0 times, it's kind of one of those strange things, right? We'd expect it's going to be equal to 1, because any number to the 0 would be a 1. But does that make sense for 0 also? Well, let's take a look at what we could do in this situation. It's going to be almost identical to the last one. It's the limit as x goes to 0 of sine x all to the x. And again, you say to yourself, I don't like the x that's up there. How could I get rid of that x? Well, the answer again is to use a logarithm. So I'm going to go, let's just say that there is a limit. And now I'll take the logarithm of both sides. So, oops. So this is roughly about where I would end up. And now I'd have to start thinking about L'Hopital's rule. This one is going to be a 0 times what looks like a negative infinity. So I'll rearrange this to be the limit as x goes to 0 of natural log sine x over 1 over x. And now I'm in the format where I would have an infinity over infinity type situation. So I can apply L'Hopital's rule to figure out what the derivatives are. This will be the limit as x goes to 0, 1 over sine x times cos x. And then on the bottom, it's going to be, let's see here, negative 1 over x squared. So I could call that the limit as x goes to 0 of cotangent x over negative 1 over x squared. So what do you think of this? What would you do before you started talking about this next step in the limit? Anything come to mind? I've probably just shot all your brains somewhere out the window after that last example. I recognize that this is a difficult topic, but I mean, look at it. If that was a limit, what would you do before you started to work on it? Give up? Go to the counselor, course change? Well, there's two fractions in that one, so why don't we get rid of the complex fraction? So this would be the limit as x goes to 0 of cotangent x times negative x squared. Which, if I put those numbers in, you can double check, but you're going to end up with one of those infinity times 0 situations again. If we think about our choices, we want to make a fraction somehow here. I think it would be nice to leave this exponent on top, because I could start to whittle it down from x squared to 2x to 2. So I know there's going to be a finale there somewhere, right? I can stop somewhere. So that's why I'm going to leave it on the top. I'm going to write this as the limit as x goes to 0, negative x squared. On the bottom then, it's going to be the tangent. And this, in fact, would be a 0 over 0 situation. So use L'Hopital's rule. I get limit as x goes to 0 of negative 2x over secant squared x. Fortunately, the torture is almost over. It turns out that it is actually 0. But again, using this technique with the logs, that's not the limit. What we found here was the natural log of y must be equal to 0. So if natural log y is 0, that means e to the 0 is y. So y equals 1. Okay, so the limit in this case equals 1 for sine x to the x. Now, I know that we're doing a little advanced stuff there, And again, I promise you that that's not the level of difficulty that I'm going to expect us to adhere to this year, but it will be reality that some of you need to jog your memory next year and go, oh God, how did I do this again? So if there's any binder that you don't chuck at the end of the year, definitely don't chuck your calculus binder, okay? Unless you'd like to torture yourself all over again a second time. But the last question, I think we can do the last one. The last one here, I'd like you to try it, work it out with the neighbor. There's not really any special techniques here. It's just, you know, see if you can recognize that L'Hopital's rule applies and see if you can come up with a limit for it. There's no logs or anything like we've already done, but just see if you can do this one. All right, so let's just finish this one here then. The first thing, and again, if it's hard to see, I apologize. Something about the resolution here is not working, but if I make a common denominator, I'm going to get x minus 1. I'm going to have the limit as x goes to 1 from the right. So common denominator will be x minus 1, take away natural log x, all divided by natural log x times x minus 1. And here, if I check, this is going to be 0, this is going to be 0 as well. So 0 times 0, and then on the top, it's going to be 1 minus 1 is 0, take away 0. So I end up with a 0 over 0 situation. So at this point, if you've got the common denominator, it's time to use L'Hopital's rule. So I'm going to have the derivatives, which will be 1 minus 1 over x. And I'm going to have to use the product rule here. So the derivative of the first piece, then the derivative of the second, which is just going to be 1 plus natural log x. And one thing I can see here is, again, I've got these extra fractions, so I'm going to multiply everybody by x to get rid of those extra fractions. So I end up with x minus 1, and on the bottom I have x minus 1 plus x natural log x, which if I substitute in 1, I still end up with 0 over 0. So for the last one, what I'll do is take the derivative one more time. So the derivative of the top this time is just 1. The derivative of the bottom will be 1, and then I'll have the product rule here. So 1 plus natural log x, then plus x times 1 over x. So those would be gone. It means I'm going to have the limit as x goes to 1 from the right of 1 over natural log x plus 2. This piece becomes a 0. That means I have a half. And I can actually use that value now. Okay. So in our world, though, you may need to apply L'Hopital's rule more than once, just like we did here. And in the other example, you may need to do it a couple of times. But you still have to check if it applies. Is it 0 over 0, infinity over infinity? Okay, so anyways, you do have the rest of the block to continue your exercises.